It all started with my analysis of a Neo-Babylonian text known as Nabnitu 32. This fragmentary text was found by Sir Leonard Woolley at the site of Ur in southern Iraq, south of the main courtyard at the Dublama Temple in the late 20s. It is Neo-Babylonian, about 600 BCE. However, the knowledge it encapsulates is certainly much older, as it describes the stringing of an archetypal pre-literate lyre fitted with 9 strings. Although most copies of this lexical series are relatively late and date from around the middle of the first millennium BCE, there is an old Babylonian precursor known as Proto-Nabnitu, published as UET 7, 3583. There are also Middle Babylonian versions dated around 1000 BCE, including one damaged copy. The document was first published by Professor Gurney in 1973 as UET 7 126 in the publications of the Joint Expedition of the British Museum and of the University Museum of the University of Pennsylvania to Mesopotamia. The tablet was returned to Iraq in the 70s. It was further published by Finkel and Civil in the Pontificum Institutum Biblicum in 1982. There are many other publications, including mine in Understanding Archaeomusicology. The contents of this text can be deconstructed in 3 layers. The first layer is a series of numbers which run as 1, 2, 3, 4, 5, 4, 3, 2, 1, a series of 9 numbers listed in symmetry around number 5. The second layer, written in Sumerian, confirms the palindrome with some variations: first, second, third, thin, fourth, small, fifth, fourth behind, third behind, second behind, behind. The meaning for the third and fourth strings will be elucidated later. The third layer, written in Akkadian, and goes as first, second, third thin, fourth EA creator, fifth, fourth back, third back, second back, and back string. I have converted the first layer into a line with equidistant 9 marks. In an arbitrary manner, I proposed apagogically that 1 to 5 was equidistant to 5 to 1, and that these intervals represented the just fifth ratio of 3 to 2, or 702 musical cents, which are logarithmic units of measure used for musical intervals. Thus, the span of the system of 9 pitches, or enneatonic, is ratio 3 to 2 plus ratio 3 to 2, equal to 1,404 cents. At present, while we can appreciate relative frequency of intervals of fifths, we cannot define their absolute pitches. I decided to apply the same principle with other intervals placed on the constant enneatonic rule, and as a consequence, I have produced an enneatonic system composed of just semitones of 90 cents, ratio of 256 to 243, just tones of 204 cents, ratios of 9 to 8, and a diminished fifth of 588 cents, ratio of 1024 to 729. This system, which some would call Pythagorean, was written far before the Greek legend would have plagiarized the Babylonian system. Nevertheless, this arrangement of pitches can be converted as a relative palindromic series of pitches as follows: G, A, B, C, D, E, F, G, and A. This palindromic scale has a series of ratios of 9 over 8, 9 over 8, 256 over 243, 9 over 8, 9 over 8, 256 over 243, 9 over 8, 9 over 8. We note that the central tritonic value is placed on the third strings of the front and on the third string of the back. These pitches would much later, at the dawn of Oriental Christianity, become known as the quilisma or stropha. However, these values extrapolated remain hypothetical. I needed to find series of numbers which would match this proposition. Eventually, I came across Hilprecht's work, the Babylonian expedition of the University of Philadelphia, Series A cuneiform texts, published in 1906. Subsequently, I wrote a paper titled Four Tables from the Temple Library of Nippur, a source for Plato's number in relation to the quantification of Babylonian tone numbers. Hilprecht's work included a series of 5 fragmentary texts which proved to be essential for the pitch quantification of Babylonian scales. Once collated, they produced the following series. As judiciously observed, Hilprecht noted that the 4 tablets shared 3 particular features. Firstly, when several multiplication tables are written together, the highest number begins the series. Secondly, the numbers multiplied are not consecutive but are often separated from each other by comparatively large intervals. Thirdly, besides 3 and 5, no indivisible number or its multiple is multiplied. Note the absence of the following numbers. Out of 81 numbers, 51 are omitted, leaving significantly 30 numbers. The fragmentary texts from which Hilprecht reconstructs one whole table throw considerable light on the whole question of their musicological significance. They all have 12,960,000, equal to 60 to the power of 4, and 3,600 to the power of 2 as their dividend. I chose numbers in the range of 36 to 81 in the red frame, since they are the only numbers in the series to produce the double fifth of 1,404 cents, since the ratio of 81 to 36 equals the ratio of 9 to 4. This span of 2 conjoined intervals of the fifth is the same which I had extrapolated from my analysis of text Nabni 232. Text Nabni 232 gives 9 pitches, while the Nippur numbers between 36 and 81 produce 11 numbers. I do not believe that this list suggested a lyre with 11 strings, but that the series would have offered a choice for the inclusion of either 48 or of 50, and excluding 80 since the ratio of 81 to 80. The syntonic comma of 22 cents would have been too small to offer any significant melodic function. This comma would only be placed for theoretical purposes. I would propose that the Nippur list held 2 different scales, the first one excluding 50, while the second excluded 48. Let us be reminded that in the text Nabni 232, both 48 and 50 are singularized in Sumerian and Akkadian, significantly as 4th small string. There is a divergence between the figure which I have extrapolated from Nabni 232 and the Nippur figures. I would explain that while the former produced a just scale, the latter were a refinement or a modal inflection of the original tonal model. I would propose that the third string, which is qualified a thin, may have been an indication of a neutral third of 343 cents, or 11 over 9. I have labeled the pitches as a G, F, E, D, C, B, A, and G, and G, A, B, C, D, E, F, G, and A, because they are close enough to the pitches of our own system on the grounds of the position of the semitones, which I have circled in red to localize them. At that point of my presentation, the pitch numbers are presented as relative and not absolute values. An A, for instance, has no frequency value. However, the interval AE is a relative fifth. However, I propose that the Nippur numbers had 2 functions. The first was to give string lengths, which might be absolute if they relate to a known system taking units of Ubanu, for instance, and the second to give frequency as reciprocals of string lengths. From 36 onward, we have a progressive increase in string length, therefore a progressive descending series of pitches, while the same frequency numbers give an ascending series of pitches. However, while string lengths might be absolute, frequency numbers are not. However, for the sake of empiricism, I have multiplied the Nippur frequency numbers by 11. This produced the following series in Hertz. It is purely coincidental that in this presentation of the Nippur numbers multiplied by 11, that A equals to 440 Hz. This is the scale given in the Nippur list. So, what is the meaning of all this? While the Nippur numbers would have produced string lengths with recognized units of length, it remains that string tension is a missing parameter without which length is pointless. If indeed reciprocals of string lengths is frequency, Babylonians did not have any device able to measure that frequency, and therefore the frequency given in these numbers was also futile. However, I would propose that while they understood these reciprocals, they could not have applied them. Therefore, they invented frequency without knowing what frequency was, apart from being of mathematical interest.